So thanks for the kind introduction, and Professor Poprave, and I also would like to thank the committee here for inviting me. It's really an honor to give the last talk in this fantastic conference here, the industrial talk on the lathe. As already said, I'm going to talk about advanced industrial laser systems and application, mainly naturally from the viewpoint of TRUMPF. And I thought I structure my talk as follows. I give a little history and some actuals on TRUMPF, hopefully in an interesting form. And then we talk a little about applications in industry, starting with CW related applications, and make a step towards solid state CW lasers. We then talk about our challenge, how we master the industrial 4.0 and the expectations our customers have to us and our answers to that. In the last part, I will then talk about short pulse and ultra short pulse lasers. Also, our old ultra short pulse lasers are never so short pulsed as Urzi's lasers, so bear with me, and then I stop with some closing remarks. So TRUMPF is clearly, as you know, we are a private family owned business. The company was founded in 1923. It's more or less came out of a machine shop and then evolved slowly to one of the biggest privately owned machine tool companies in the world. It's today split in mainly two divisions. It's a machine tool business and a laser business. Laser business takes revenue-wise around 30% today, and we are spread over 73 subsidiaries worldwide. And one thing that is driving this company and always fascinated me before I even joined TRUMPF is this continuous drive to new innovations, and that has poisoned the company, I think, since its beginning, mainly also driven through Berthold Schmidt. I thought I sneak in some financial data here in the way that I present it on a log scale. So you see here the revenue development from the TRUMPF organization since 1949. Obviously, it's easier to grow your company on a rate scale along. It's still in the millions and in the billions. TRUMPF has put a lot of effort to grow their organization over the decades with new technologies. It's surprising, but already in 1979, TRUMPF introduced the TRUMPF system, which was already a punching machine together with a laser cutting head by that time with 500 watt. Then the industry demanded higher power levels. Kilowatt CO2 lasers were not available by that time, so they started to make their own CO2 RF powered kilowatt level lasers. They were introduced first time 1985, 1989. The folded cavity lasers, CO2 lasers, were introduced that are still the building blocks for our today's CO2 laser architecture. And then already in 1999, 2000, the first disc lasers came to the market out of the TRUMPF product portfolio. Now, today, TRUMPF is naturally investing heavily. I think Peter Leibinger mentioned this morning, we're investing around $400 million in R&D every year, or last year at least, and into new technologies such as fiber laser activities, additive manufacturing, as you saw in the introduction, and also Axum, a software-based system organization that is supporting the industrial 4.0 activity from our customers, and also the EUV business. And I think the EUV activity is a good starting point for my talk, because it gives another nice example for the entrepreneurial spirit of the TRUMPF organization. This activity was started 10, 12 years ago, mainly inspired by Peter Leibinger, supporting this very heavily. The idea is really to use a CO2-powered lithography system, more or less to generate the next generation of microchips with knot sizes below the 7 to 9 nanometers we have today. And this is done in a fairly simple way. So I skip difficult equations. You use a CO2 laser. You hit with a CO2 laser a tin droplet in a chamber. When you hit it precisely and strong enough, it creates a plasma, and the plasma then, during the regeneration process, emits light in the range of EUV 13.5 nanometer. You use the CO2 laser because the absorption coefficient in the plasma is proportional to the lambda square, so longer wavelengths actually helps here. And then you guide your EUV light through a set of optics and masks onto your semiconductor wafer. Naturally, the whole thing is a little more complex than it's shown here. The droplet generator that is used is already a technical challenge, creating 50,000 droplets per second, so we have to hit each droplet with a frequency of 50 kilohertz. Actually, we have to hit it twice. So first, there's a pre-pulse, and we create a small mist of particles. And then with a second pulse from our lasers, who has already a size of a house, it's actually a diffraction-limited laser to create this plasma. And then the lithography system, which normally unfortunately stays in these fabs on the top, our lasers in the basement, it has roughly the same size, guiding the EUV light onto the mask. So looking at the laser a little more in detail, as I already said, it's a 30 kilowatt laser. It's a MOPA system, master oscillator power amplifier. We are creating a plasma temperature with that of around 500,000 degree Kelvin. And just to give you an introduction on the architecture, you see the 4-stage MOPA laser. I think it's a very nice example how, from a very fundamental idea with a continuous investment and growing with your partners, we evolved this from early stage development into a real product over the years. So, unfortunately, the world is changing, and I think that's a very good example, because this kind of describes the ratio of CO2 lasers and solid-state lasers we are selling out of the laser business into our machine tool business. So you see that just within the last 10 years, there was a fundamental change in the industry, and it was a real challenge to manage this technical drift away from CO2 lasers towards solid-state lasers. Solid-state lasers for cutting at 1 micron have naturally the advantage that they are less sensitive to plasma absorption in welding, for instance. So that's why they are easily going through the plasma plumb that you normally have above a metal workpiece, and therefore CO2 lasers are great for EUV plasma generation, and the solid-state lasers are better for welding and cutting purposes. So this change we approach with a whole bandwidth of technologies, and you see this here with our international entities. CO2 lasers are still manufactured very successfully in Ditzingen. Schramberg is doing the disc laser activities in Germany. We have a marking laser activity. The diodes and the pumps are produced in Princeton Photonics. That's the area I'm active right now. We are supplying SPI in Southampton that is now, together with JK Laser, we acquired. Then there is this group in TRUMPF Scientific in Munich, and then there is our engineering group that is providing us the micro-optics for that. And we are more or less supplying out of our entity most of those activities. And then there is still a little space. You might heard that we just acquired another company in Aachen, Amphos, to complete our technology portfolio. You see, we're not picky just on one system, and I think that's a great acquisition, because on that we will have additional synergies for future laser systems. So one slide on diodes. So we are, as you know, that in Princeton we are continuing this vertical integration activity to be successful. We have various building blocks. We have here the pump system for our disc lasers, that the bar power went up over the years to 180 watt, and now in the latest disk laser architecture to more than 200 watt on the operation level naturally. We are using an isolated elasticooler for those bars, and this is also a very handy tool because the same lasers, the same concept we use for our research activities on the dense wavelength multiplex systems that is shown below here. The whole same line is also producing in higher and higher volumes single emitter and fiber pump modules. That's a 14 emitter module with 140 watt output power. In general, it's an industrial standard already, and we are supplying this to our entities naturally, SPI, but also for marking laser activities and some short pulse fiber laser activities in Schramberg. Now, talking about some applications on the laser side, and I stick a little with the ZW applications. Our customers, they expect that our system has a very high flexibility. So with the same machine, we are able to cut this small bicycle with those feature sizes in the micron and millimeter range. We are also cutting then these thick steel plates, and that's what our customers expect because those smaller companies, they have a whole variety of orders and challenges therefore. The other applications we don't actually have is cutting of transparent material, marking, then laser additive manufacturing on the one side, the laser deposition, and the laser melting out of a powder bed. On the abrasive technologies and on the automotive technologies, our lasers you can find in mainly in the automotive industry. There was a big change now in the automotive industry. In particular, this came due to the introduction, I think that's a very nice part here of the presentation, introduction of various steel levels that can only be processed by means of a laser. So, and when you start using a laser in your production line, then you naturally also need to precise cutting your other laser areas. So you suddenly, it's like a domino effect. You start introducing your laser in multiple production steps, and therefore we saw this enormously increase in welding and cutting lasers during the past years in the industry. When we span more or less the use or the utilization of lasers in a matrix, and I think you have seen this in various forms already, I don't stay here for too long, then you see that the markets we have is remote welding and cutting, but also, let's see if I have here. Yeah, so we have here, this is the biggest and most dominant market with remote welding and cutting. There are other applications at lower brightness levels when you go up here with a BBP that are still sufficient for conventional laser welding, but also for brazing surface application, naturally with lasers that are beyond 12, 14, 16 kilowatt. You can do applications like deep presentation welding and hybrid welding. To satisfy these expectations from our customers, we have a whole variety of different products we are utilizing for those purposes. And fundamentally, the technology is based on those platforms that are shown here, while the rod laser is not anymore due to its disadvantage of having this heat profile and or the cooling and pumping in the same range, and therefore the heating up and not being any more prominent for high power laser systems. So being a diode person, I know that improving a laser diode or the power level of a laser diode, you normally reduce the confinement factor, you bring the internal losses down, and then you just enlarge the footprint of the laser device to have a better cooling. And you can do actually the same thing naturally with a fiber laser and a disc laser, reduce doping concentration, enlarge mode size, diameter, and therefore for fiber, for instance, just enlarge the length of the active fiber. on the disc laser, you're enlarging more or less the ratio of the surface to volume. That's why we use a thin disc laser. And I like the disc laser in particular as a diode person because it can be pumped with a low brightness laser diodes just in the range of 450 millirad. So it's for a semiconductor laser diodes, it's really like a flash lamp. And it's a great brightness converter, as you will see in a minute. So those technologies we are more or less selling to the market. And here's the matrix that more or less fits the matrix you have seen before. And is there a better pointer? No, okay, it's not much brighter. So the fiber laser activities you see here, we have today standard products are up to 1 kilowatt high brightness. Then the disc lasers, these are coupled into 100 micron. They're going up to 12 kilowatt. These are folded disc lasers, so there are 2 disc lasers in the resonator. Thank you, you're fantastic. And then we have even higher power disc lasers. And then you see here our conventional direct diode laser systems that range from brightness levels of 30 to 50 millirad. And naturally, there is an activity going towards bringing those down. But first, let us look at the single mode or single disc achievements we have already published. There was a very interesting paper 2 years ago from our team in Schramberg that showed kind of almost single mode disc at 4 kilowatt that was pumped with 969 nanometer into the zero phonon line. Today, products we are having are more in the range of 8 kilowatt. That is the next product we're going to release on single disc level, and the capabilities go up to 11 kilowatt out of a single disc already. So the product portfolio is naturally added by the lasers from SPI that also have power levels of meanwhile up to 8 kilowatt into 100 micron fibers. And when we see what we're doing here with our test activities, you might have visited our booth. We are showcasing there a 2 kilowatt dense wavelength multiplex laser. Those lasers are normally coupled into fibers of 150 to 200 micron. So it's still in the engineering phase, but I'm very positive that that will be an interesting add-on to support the laser portfolio we are already cultivating. Disc lasers, I want to just stick with that a little because in particular they're important for our short pulse activities. They have this beautiful purpose or property that they have these thin discs that are glued on a diamond, and therefore we have this unnatural heat flow giving us a very low thermal lensing for high brightness, even at very high output power levels. And I already mentioned the low brightness constraints of the laser diodes. The laser operates at a very high gain saturation. So when you have a CW laser at 6 kilowatt, the output coupler has a reflectivity of 97% in the range, which means there are 194 kilowatts stored in the cavity. So this makes the disc laser very insensitive to back reflections, thus being a very robust industrial laser for cutting all types of steel and materials. And the negligible nonlinearities are in particular helpful for achieving very high peak powers, as you will see in just a few minutes. So this is our last generation of disc we are now bringing to the market. The team has enormously improved the system. We are achieving now an optical to optical efficiency in the range of 71%. You see here the result with around 11 kilowatt out of a disc. This laser then allows us also to achieve disc laser systems that are almost reach 40% in volt plug efficiency, which is, I think, a tremendous step forward also for this technology. So you see here, it's more or less the pump light, which enters here through this window, and you see here is the active disk. It dances around between those prisms and the parabolic mirror until it's getting fully absorbed in the disk, and then we have we are generating more or less the laser beam here out of the disk laser unit into the resonator. In comparison to direct dyed laser diodes, you see the footprint is fairly similar, and I use the old format of which is still our biggest volume product on the disk laser side, because you see here the pump units with the semiconductor bars included, and our direct dyed lasers, which have these higher BBP, so 30 to 50 millirad, they're the same platform, which is important in driving these volumes and bring the cost down for our customers. So you see here direct dyed laser with 45% power conversion efficiency as compared to the previous generation of disk lasers. And to give you an idea, those direct dyed lasers are created by wavelength beam combining here, 3 wavelengths, then spatial beam combining, and naturally coarse wavelengths or polarization beam combining to combine 2 of those modules. And with that we achieve 6 kilowatt and out of the system. And if we go now to the next generation, these are our activities around the dense wavelength multiplexing. There the bar on an Elasco is more or less wavelength stabilized within an external resonator, and then we use a diffractive element. You see here the spectra of the bars within one resonator, so each emitter is actually operating at different wavelengths, and then utilizing the diffractive element, we can overlay them onto one single laser spot. And we showcased one system at the laser show in Munich. This was a 4 kilowatt laser, and you see outside there another one at 2 kilowatt we have at our booth. We can drive this forward because naturally the laser, the brightness of a dense wavelength multiplex laser depends really on the beam quality of the emission bar. And there was an interesting paper from our group in Berlin showing a single mode bar with, I think, 200 emitters operating all now here at different wavelengths, and achieving in this lab experiment already 100 watt out of this bar with an M square that is already stabilized within a resonator with an M square of 2. So this should give us then long term also the opportunity to couple direct dyed lasers into 30 to 50 micron fiber diameters. So now let's talk about something completely different. The challenges we have with the industry 4.0. Our customers, we like the technical details. Our customers expect that we are going to stay on top of the technical development on the laser side, but on the other side, they also want to use this in their production environment. And that is very important because there's a lot of research going on to make those systems ready to be used in Industry 4.0 environment, which means in general our customers want the systems to talk to each other. They should have maximum flexibility. So you want to optimize the laser on time. You have switches, beam switches, power sharing in your systems, and this should be all controlled automatically. On top, you want to use your laser as a smart manufacturing tool. It's more or less our lasers so far have a brain, so to say. So they have, if you keep in mind that we are generating something like 500 data points during a cutting or a welding process, it's very important to use this data to support our customers during their production cycle. So these lasers are then fully maintained. We have a software, we have an overview we're receiving into our systems. We look at the program changes our customers are doing, and we call them if we see that the lasers have a fluctuation or maybe a lens getting contaminated, and all the data is naturally transferred over a secure network. That's why we have Exum, and then the data comes into our condition monitoring center, and we analyze the data, not the process data, because that belongs to the customer, but the condition data from the laser. And when we see a fluctuation, or we see that the product maintenance is required, we call the customer. Either he can do this on-site, or we go there directly to support the customer, which is important when you think that there are factories that have 20, 30 lasers of us standing there operating simultaneously. Each laser is responsible for a particular process step. We have to assure that we have 100% on time in those factories. Now, let's go to the last part of my talk, talking a little about short pulse and ultra short pulse laser systems. That is a very important driver for our future growth as well. Keeping in mind what you can do already today with all the short pulse lasers in industry. You see here some applications: laser marking, cutting of cover glass, thin film ablation, cutting of ceramics, laser annealing, laser lift of sapphire cutting, and all of those applications can be more or less supported by means of solid state laser systems. I give you an idea of that in a minute. So, and then on top, we see also the opportunities in the e-mobility market, where also a lot of our lasers are utilized. All those markets are projected to grow in the next year with a rate of more than 10% per year. So I think that's really an important field for a company like TRUMPF to be present. To give you more details, this is now another revenue picture. This is again all the OEM lasers the TRUMPF organization is selling into the market, and you see how since 2006 the number of true micro lasers increased dramatically, together with the overall increase in volume over the whole product portfolio, and that is mainly for those type of applications: marking, engraving, code processing, ablation, and rapid thermal processing. We have distinct laser systems who are doing those type of jobs. So one laser is the regenerative thin disk amplifier. It's again a fairly straightforward methodology how it works. I better explain it on the next slide. So we have a seed laser coming from a fiber laser seed that is entering the regenerative amplifier, and then it's locked in the amplifier because we then switch the pocket cells off, and then in that moment the seed is more or less always getting amplified and entering through the disk around 100 times. It increases in magnitude 5 or 6 times to the order of magnitude, and then when we have this power, it's getting, we turn on the pocket cell again, and then it goes through an RAM directly onto the workpiece. So these laser systems, the regenerative amplifier systems, are picosecond lasers. They are having a power level of 150 watt in the infrared. You can have them also with second harmonic generation, and then when we throw in chirp pulse amplification on it, they go in terms of the pulse length into the sub-picosecond range of 900 to 700 femtoseconds. The application of those is mainly for cutting and working with transparent materials. We combine this, and this is another important example with our top cleave optics. If you could maybe quickly start the video, and then can you click on that? Oh, no. Okay, so it obviously doesn't work. Oh, now we are. Okay, so the top clip optics is in general a technology where we use a diffractive optical element to create a bezel beam, and this bezel beam then is able, here we go, to, this is still using an ablative scanner cutting with a standard Gaussian beam. Now you see here the DOE, how is it formed, and this DOE with a focusing optics creates a fine bezel beam that creates more or less a distortion in the material when you move it with a picosecond laser through the material, and this material modification then is creating more or less an additional strain in the Gorilla Glass, for instance. And now you see it in real time here. It's actually a pretty fast process, and you just have to go through the material once, and then you just put it there, you wait or you blow on it, and due to the chemical stress in the glass, you get your cover glass out with any burrs or additional particles. So it's actually a very nice process. We are playing around with, naturally, with those bezel beams a lot. For instance, in the future also to create chamfers on the side of the glass, and this is a different DOE we are using for that. And actually all those technologies I should mention are also coming already with Kagome fibers as beam deliveries for those picosecond lasers. Another family of our short pulse lasers are the nanosecond pulse lasers, and again we utilize the disc laser, the thin disc laser technology for that. The key applications are on the one side laser liftoff, which is our predominant application for those technologies, and tomorrow's application with even higher powers from those nanosecond pulse lasers is also then solid state laser annealing, where you more or less transform amorphous silicon into crystalline silicon. You can then bring up the pixel size on your OLED displays, and without harming more or less the rest of the material, or to have to heat it up, which is right now a predominant process for the excimer lasers in the market. So the technology for the liftoff is fairly simple. Our lasers in the third harmonic generation has a wavelength of 343 nanometer. We are going through the cover glass and destroy more or less the glue that is between the OLED and the carrier glass that is used for the whole production process. And you see here the various generation of glass sizes that are already used in the industry. The UV line beam then destroys this glue, and then you can just slip off the OLED display after your production cycle. So for that we are using a cavity dumped laser technology, which is even more simple than a regenerative amplifier. It's in general just a laser where you more or less lock the whole light in your cavity. You let more or less the power in the resonator go up, and when the power level which is detected by this photodiode reaches a certain limit, then you switch your pocket cells and you release your laser pulse. Laser pulse has naturally the length in terms of the round trip time of the resonator, and therefore it's in the range of 17 to 20 nanoseconds. And then you can more or less cascade the frequency conversion here with your crystals on two stages to avoid that you're not having too high power densities in one single crystal. And with these architectures, we are already achieving up to 400, 500 watt out of a single laser. Let's just, to the end of my talk, I just want to give you a few ideas of our future concept. One of the things we are working on is actually to enhance the power level of our short pulse lasers with by means of a multipass amplifier. Multipass amplifier is a fantastic tool. It more or less just brings a laser from, for instance, a cavity dumped laser system and let it dance around the disk. Since the multipass amplifier doesn't have any absorbing materials in there, just an amplifying disk, the B integral is very reduced, so we don't have any distortion of the pulse and of the phase. So it's really just a turbocharger of our lasers, and with that we achieve extraordinary high output powers. For instance, with the nanosecond system I just showed you before, we are achieving here out of the multipass cell 2 kilowatt, together with the cavity dump 1 kilowatt system. In infrared we already reached 3 kilowatt of nanosecond pulse laser output power. You can also apply this technology to a CW laser system. Here, together with a single disk 7 kilowatt disk laser, we are getting up to 20 kilowatt out of this laser system, which really just consists out of one single disk and the multipass cell. And then we can naturally apply this technology also to picosecond lasers. You see here the picosecond laser TRUMicro 5000, and with a multipass cell we are planning, this is an activity we have in a Euro-funded project, to go up to 1 joule pulse levels, the picoscale, which is equivalent to roughly a terawatt of peak power in a picosecond. So I'm gonna end now with some closing remarks. So I hope I was able to give you a little of an understanding why it's for us so crucial and important that we are supporting various technology, various platforms. You saw that new applications like the laser liftoff in large scale or laser surface annealing is so important for us, and that's why we continue to drive our ultra-short pulse technology forward. Long term, we see, and I think that's also an important statement, various platforms existing in parallel, because our customers have always slightly different needs and demands. And I think the laser development, what we see in industry and working with our partners at the various institutes, has clearly not ended yet. Just as an example, going back to Switzerland, we are planning to install on one of these projects, just on the last architecture you have seen, a laser on the Centis, and with this laser we create a kind of laser lightning rod, because when you fire it, you create a plasma filamentation in the air, and during a thunderstorm you can then shoot down sparks and the lightning, which is also interesting to protect airports long term for arriving and departing airlines or airplanes during a thunderstorm. Okay, with that I'd like to thank you for your attention.